Good afternoon, everyone. Thank you very much for coming and coming to our colloquium today. It's my pleasure today to introduce our colleague Oren Etzioni. Let's see. There's so many things I could say about Oren. It's hard to resist saying them all. I'll just start with, Oren's known for so many things, and he's especially been doing some innovative work on the semantic web of late. I guess what I wanted to say, in reflecting back on my years of collaborating with Oren, it's been such a pleasure because he knows so much. But he has high aspirations, and we see today that he's not going to stop there.
Thank you, Dad. Thank you for coming. Those of you, please feel free to come down. I'm going to be talking about our KnowItAll project, which is ongoing work since 2003. But before I start, I guess you could call this a word from our sponsor. I wanted to mention that this work is being done under the auspices of the Turing Center, which was founded in May of 2005 with a generous gift from the Utilika Foundation. And the Turing Center is investigating a variety of problems in the crossroads of NLP, machine learning, search, and the semantic web. There are two main thrusts to it. One is focused on panlingual translation, and I won't talk about that today. And the other one is the KnowItAll project. They're actually interesting points of intersection, but my focus for today will be on the KnowItAll project. I also wanted to acknowledge not just my colleagues, but as this is one of my favorite quotations says, also my students. So there's quite a number of people who've worked on this project over the years, and they're color-coded. In blue are folks who've been hired away by a search engine company. It's a professional hazard if you work on this kind of stuff. In gray are folks who moved on to, how shall I put it gently, substantially less interesting research topics, and but still very worthwhile, I'm sure. And in bold are the folks actively working on the project today with me. So the motivation, and some of you have heard these, so I'll go through it quickly to get to some new stuff. But the motivation here is twofold. First, we're interested in very fundamental AI questions. How do you accumulate the kind of massive knowledge needed to build an intelligent system? It's a very hard question that very few people are working on in AI today. Our hypothesis, which we're investigating, is that you can do that automatically from text, like the text you find on the World Wide Web. Effectively, we're asking, how can we build a program that reads, at least at some shallow level? Another question, which is closer to hand, is what will web search look like 10 years from now, or even 5 years from now? Is it going to look still like Google with typing a few words into a search box and getting a list of results? Or can we imagine a much more powerful interaction? Can we imagine information extraction, the ability to go into text and take factual elements out of that text? Can we imagine that as the basis for a new kind of search engine that's much more powerful? Imagine asking it something like, how's the ThinkPad T-series, and getting a response like, well, I found 2,300 reviews. I've analyzed them for you. 85% of them are positive, and the highly rated features are these. And you can go on, and what people are saying about them is that, and here's how it compares to the X series, and so on, right? So this is synthesizing information across multiple web pages, potentially a very large set, and putting it together to give you an answer to your information need. And actually, Anna Maria Popescu built a system that does an element of that with very high precision. It does all this kind of analysis and more, and that's a paper that appeared in EMNLP last year. I'm not going to have time to talk about that system called Opine, so I encourage you to read the paper. But this will serve as the outline of my talk, this family tree. So I'll start out by talking about KnowItAll, our system, and I'll show how it led us to build a system called the binding engine, and also led us to explore a combinatorial model, which we're calling the Urns model. These two pieces together form a new system called KnowItNow, which I'll demo to you. And then that's led to our latest and greatest, which is TextRunner, which I was going to demo to you, but I think it crashed shortly, and now it's back up. So if I'm feeling, we'll see if we have time, I'll demo that as well. Okay. So how does KnowItAll work? It really has a very simple generate and test architecture. The basic idea is that sentences contain clues as to their meaning, syntactic clues. So take the sentence, cities such as Boston, Los Angeles, and Seattle. It contains a clue that Boston is a city. Okay? And this isn't about cities. It's a general phenomenon about English, and there's corresponding ideas in other languages as well. If I see something that says some class name, such as a series of noun phrases, then I can at least conjecture that each head of a noun phrase is a member of the class. So Boston and Los Angeles are cities. Now, this gets tricky in a hurry. Take this sentence, detailed information for several countries such as maps. Well, maps are not an instance of countries, so we want to restrict ourselves to proper nouns. That turns out not to be good enough. Here's a sentence, I listen to pretty much all music, but prefer country such as Garth Brooks. Now again, Garth Brooks is not a country, so these mechanisms are very much imperfect, right? They generate candidate extractions, and the next step in the process is to test them. And the idea of testing them is to assess them using the mutual information between what we've just extracted, and I'll go through an example in a minute, and some phrases that we call discriminator phrases. These would be phrases that are indicative of something being a city or a country or whatever is the concept of interest. So if we have high mutual information between the extractor and a set of discriminator phrases, then we're more likely to believe that the extraction is in fact bona fide. Okay? And Turney, in an influential paper in 2001, pointed out that these mutual information computations can be done very efficiently over the entire web corpus by using search engine hit counts. So this idea boils down to repeated iteration of a very simple thing. You query, let's say if you want to know if Yakima is a city or not, you would query Google, say, with Yakima City, and you'd query Google with Yakima to normalize your results, and you see what fraction of the time is Yakima co-occurring with city. And you do that a number of times for different things that are indicative of something being a city. Maybe you use the phrase mayor, or maybe cities such as Yakima, and you get a pretty good idea very rapidly. Is Yakima behaving as a city in your corpus? And you know, no comment about Yakima actually in the real world. That's beyond our scope today. I have no idea. Okay, so here's what this looks like in a little bit more detail. If I issue Yakima to the Google index, I get 1.3 million hits roughly. And if I use as my discriminator phrase the class name, so then I also issue the query Yakima City, I get 2760. And the PMI here is simply the ratio, 0.02. If I repeat this with avocado, which as far as I know is not a city, avocado appears in the index 1,000,000 times. Avocado City appears in the index 10 times because pretty much anything, right, appears in the index a few times at least. But if we compare the PMI scores of avocado and Yakima, we see that Yakima is much more likely to be a city than avocado is. So that's the kind of computation that we do. There's a lot more complexity here, and I won't go into a lot of the details. They're in our papers. Nevertheless, let me just walk you through the sequence here really quickly so you see how these pieces fit together. So KnowItAll takes as input a set of these generic templates like X such as Y, or the R of X is Y. And it takes some set of relations of interest. What am I interested in learning about? CEOs, cities, etc. And then it instantiates each template with a relation. So it might say, OK, I'm going to find CEOs of companies using the extraction template, the CEO of X is Y. It turns that into a query to Google, the CEO of, gets a bunch of pages, extracts the relevant sentences, goes through them, and extracts candidate pairs, right, of CEOs and companies, X's and Y's. And then it automatically creates a set of discriminators, D sub I, from the templates. It does these PMI computations I mentioned. Those turn out to be feature values which are fed into bootstrap naive Bayes classifier, which is what we use in the assessment. Specifically, we use the naive Bayes classifier to combine the evidence from these different discriminators. And I won't go through the details here. Finally, we have an assessed extraction, which we put into our database. So this is what it looks like, and this is available over the web if people are interested in playing with it. We have a variety of relations, and we have a set of extractions and at least crude estimates of probability associated with those. And here's a more concrete example. Steve Ballmer stopped by, and Ed had me meet with him for about 2.5 minutes, and I wanted to reassure him. And so I showed him that with very high probability, he is indeed the CEO of Microsoft. And you can see, if you look at the details here, you can see there's 51 justifications for it, and the details are available, so you can drill down and see the actual text this was extracted from. Okay, so often when I give this talk, people say, wait a minute, but what about time, right? Clinton's the president of the United States, but that statement was true in 1996. It's not true today. What about context? One of my favorite misunderstandings of the extraction systems we've been building is you ask it, who was the first American in space? And it says John Glenn. And if you go and drill down, you find that that comes from a page entitled Common Misconceptions About Space. So the system will happily believe that. Or matters of opinion. If you ask it who killed JFK, it'll come back and say Elvis, because that's a popular answer on the web. So another issue is multiple word senses, right? On the web, again, if you, quote, listen to the web, you think that Amazon is a bookstore, not a rainforest, and Chicago, Chevy Chase is an actor, not a suburb in Maryland, et cetera, et cetera. So all these are largely unsolved problems for us, but from my point of view, that's great, because these generate research problems for students at all levels, and again, invite you to join us and work on these problems. Nevertheless, we do have pretty good precision. So here's an example for some unary relations, city, country, and US state. And you see on the x-axis recall, on the y-axis precision. I won't define those except to say that the more of each, the better. And you see that the precision, basically the accuracy of the system, is very high. If we go to binary predicates, like capital of or CO of, again, we see pretty good results. Now, it turns out, though, that recall isn't that great. So how many CEOs do I actually get? How many cities do I actually find? Turns out it's not that great. So our next step in building KnowItAll is we identified 3 methods for improving recall. One is to automatically learn extraction patterns that are specific to the relation of interest. So for example, headquartered in city is not part of our generic templates, but it's very helpful for extracting city names. And we can learn that by bootstrapping from the city names that we did extract initially, right? So we had generic patterns, gave us some elements of the relation. Turns out it's easy, once you have a few examples of a relation, to find these relation-specific patterns like headquartered in. A second idea is to make the extraction process recursive. So if I ask you for some scientists, it turns out you don't see a lot of sentences, scientists such as X. You might see a lot more sentences of the form physicists such as X or chemists such as X. People are usually referred to as the particular kind of scientist that they are. Well, that's no problem for us because we can be recursive. If we find a sentence, scientists such as physicists, chemists, and biologists, we can start to build a hierarchy, right? Where scientists at the top and physicists are below that, and specific individual physicists are below that. And we can use inference to start populating and understanding who's a scientist and who isn't. The third method that we use is going out on the web and finding lists of items. And this is similar to Google Sets, if you're familiar with that. And it turns out that, again, once you have a few examples, you can just query with the example names. Query Google with Boston, Los Angeles, Paris, and Nairobi. And what you'll find is it returns lists of cities, right? And so we accumulate actually a large number of these lists. And we, on the fly, learn how to extract elements of these lists. And then, again, we collect them up as extractions. And these methods all enhance the recall of the system, the number of items it's able to extract. Usually at this point, I ask which one of these do people think works most effectively? But some of you have heard this talk. So those of you who haven't heard the talk, any guesses as to which one of these would works probably an order of magnitude better than the other two? You've heard the talk. You did some of the work. Tom? That's right. So it turns out there are lots of lists, and they allow us to extract thousands of elements from a single page. So that's, again, a very handy tool. So here's the bad news, okay? We have precision, we have recall. I could walk off right now, except that it turns out that the system, and this is our dirty little secret. I never revealed it until we actually solved this problem. Our system was really, really slow. Turns out that Google queries, right, are necessary for both extraction and assessment here, right? And we can't just hammer Google with queries. We space them at least once every second to give Google a chance to serve the rest of the planet. And so experiments here can take weeks, right, which isn't fun, particularly as you're approaching the paper deadlines. What's probably even a more serious concern is that Google bounded us with a very generous quota of queries, but nevertheless it's bounded, right? And we're trying to be know-it-all. And so we're never going to know it all. I once computed how many facts we were extracting per week, and I realized very quickly that we weren't even going to know some of it all if we didn't come up with a much more scalable system. And so the solution is, why don't we use our own private index of the web, right? Moore's law has made it the case that it's actually not that hard if you have a modest cluster of machines and a few disks to build a private index of at least a non-trivial fraction of the web. So the disadvantage of this, we will have a limited index size, and that's something that we need to deal with. The other disadvantage, though, is that even if you have a private index, turns out this extractions process is still pretty slow, because the thing that's really gating scalability here is disk accesses, specifically random disk accesses, right? If you move the disk head, that's a very slow process compared to everything else we talk about here. And so we want to minimize the number of random disk accesses. And so Mike Caffarella had the idea, well, why don't we build a search engine that takes queries not just containing strings, but also containing typed variables. And it turns out, as I'll show you in a second, that's very powerful for the kind of extraction that we want to do. So this search engine called B, for bindings engine, can take a query such as President Bush verb, and it'll return in sorted order by frequency all the verbs that follow President Bush in the corpus. Or if you say cities such as head of a noun phrase, again, it'll return to you all those candidate cities, right? So you can see with that kind of language, we can build extraction machinery that's very powerful. I mean, you can express much of KnowItAll actually as a small number of queries to this system. And the most clever thing here, which I won't have time to talk about, is actually that the indexing here is done such that the disk accesses are completely sequential, right? So this is much faster, as I'll show you in a second. So we did an experiment comparing B to a local installation of Nutch, the open source search engine, and we were, in this particular experiment, 136 times faster. If you look at the complexity analysis here, you see that actually the difference is even more profound. So let's define my terms. Let D be the set of documents in the index, and B be the set of bindings that are returned in response to one of these queries. So that's like the set of cities in our example. T is the number of terms in the query. So if I say cities such as noun phrase, T would be 4. Now let's look at how B compares to a standard search engine. First of all, let's look at space, because B is implementing a space-time trade-off. It turns out that B's indexing is only a constant factor more than the standard index. So the standard index is linear in the number of documents, and so is B. That's good news. And that overhead is actually very manageable. For example, if we only restrict ourselves to syntactic types such as verbs and nouns and modifiers and so on, then it's just a factor of 2 increase. Now, when we go to query time, we see where the real win is. So we're counting here, again, these random disk seeks. B does order T, and T is very small. A standard search engine would do T plus B, and again, B is very large, right? B could be easily 10,000, right? So if T is 4 and this is 10,004, you see the kinds of speedups that we get, and the bigger the index, the bigger B is, the better we do. Okay, so this is a substantial advance. Are we done here? Have we sped up the process? Well, the answer is no, because I didn't talk about assessment yet, right? Assessment is done using these hit count computations, and we do those over multiple discriminators. So we still, even though B's extraction is fast, the PMI computation is slow, and using 10 discriminators will result in the order of 10 queries to the search engine, and these will not be sequential, and things are bad. But we had the following insight. PMI, what is PMI really doing? What is this notion of mutual information? What it's really doing is simply counting co-occurrences of phrases in text. And so we said, well, why don't we just count the co-occurrences, but instead of doing it in Google's index, let's count the co-occurrences in B's output and use that information for assessment. And I'll show you in a few minutes how that plays out, but I want to take a segue and talk about another important idea, which is, okay, we have these counts, but how do we map them to how sure we are that the extraction is correct? Okay, that's something I glossed over earlier. And again, I won't go through all the details here, but I'll give you some of the flavor of that. So this is work by Doug Downey, Stephen Sutherland, and myself. There was a paper at IJCAI. And it's a probabilistic model of redundancy in text. Let me give you the intuitions. If we see something multiple times in independently authored documents, we begin to believe more and more that it's true. Again, not world truth, but true relative to what's said in the corpus. It's not some error of the extraction machinery or the parser or something like that. So, for example, if I see the phrase Atlanta and other cities 980 times in different documents, that starts to increase, all other things being equal, my confidence that Atlanta is indeed a city. Now, and I'm going to believe that it's more likely to be a city than Canada, say. And again, you can normalize these figures in various ways to make this even more accurate. Now, the second intuition, which is also important, is that there are ways that people speak that could lead this kind of machinery astray. So if we look at multiple distinct extraction rules, different ways of saying things, and in those different ways of saying things, again, Atlanta reliably appears as a city. Not only Atlanta and other cities, but cities such as Atlanta, again, that increases my confidence even more. And it turns out, for example, with Canada, suddenly people don't say cities such as Canada hardly at all. And so we start to see that Atlanta is much, much more likely to be a city. So those are the intuitions. How do we develop a formal model of these? The natural thing to go to is what's called the noisy OR model. Let me see if I can give you the intuitions here. Here, let's take an example where we're trying to extract countries. And we have 10 sentences that have been extracted. And these are the extractions. Saudi Arabia came up 2 times. That's the variable k, et cetera, et cetera. And we get to Africa was extracted once as a country. And we ask, what exactly is the probability here that Africa is a country based on the fact that I saw it once in one of these extraction rules? Well, that probability is a function of the extraction rule's accuracy. Let's assume we've estimated that from previous experience with that extraction rule, right? These are generic. So when we were playing with cities or something else, we found that it's about 0.9. So we're going to believe that the probability is exactly this expression. The probability that x, the extraction, belongs to the class C, given that x appeared k times in the extraction set of this rules, is simply this expression, which is basically 1 minus the probability that the rule is wrong k times, right? So if I saw the extraction in the rule's output k times, all those k times would have to be mistakes for the rule to be wrong, or sorry, for it to not be a country. And so that's this expression. And we subtract that from 1 to get the probability that, in fact, it is a member of the class. And if that went by too fast, it would have for me too, unless you're already familiar with the noisy OR model. But that's not our model. That's actually turns out to be the standard model used in previous work, and it turns out to be a lousy one. Why is that? Well, it doesn't take into account several key elements. I'll just talk about one. It doesn't take into account the sample size. Okay? So imagine that instead of these 10 extractions, imagine that, okay, so these are the probabilities that you get out of the noisy OR. Here, again, Africa is 0.9. That's reasonable right now. But now imagine that instead of 10 extractions, I did 50,000 or 500,000 extractions. And still, I only saw Africa once. In this model, the probability doesn't change, simply because if you look at this expression, it's not a function of n. Okay? But the more extractions I get, with Africa staying at 1, the more likely it is that this was just some kind of strange error, right? Particularly if, again, I can check and see that Africa is a pretty frequent word on the web. It just occurs very infrequently in this sample. So noisy OR model ignores sample size, and we need to find a model that doesn't. And so our idea was to build a combinatorial model. It's a variant of a classical balls and urns model. And let me show you a little bit of how it goes. So this urn represents the set of extractions you would get from some extraction rule. And you'll see that some of the time, it doesn't matter which one, but it's an extraction rule for cities. So some of the time you'll get Tokyo, which is correct, and the red ones, the red balls here, are incorrect. Okay? So so extraction is really drawing balls from this urn. And we see that balls are repeated, right? So the balls, distinct balls correspond to distinct sentences, but you can have 2 sentences with the same name in them. Okay? So extraction is going to be drawing balls out of this urn with replacement. A little bit more formally, if we let C be the set of distinct correct names, E the set of distinct errors, and num be the number of balls named by either C or E, and then num of capital B is the distribution giving the number of those balls for each B, then it turns out that A, we can estimate this distribution via EM, and I won't go through the details of that, but most importantly, we can now write down an expression, a precise expression for this question. If an extraction X appears K times in a set of n sentences that match some extraction rule, what is the probability that the extraction X is a member of the class? And it turns out to be this very simple expression here that I'm sure nobody understands. It's a fact. Probably more interesting is that with some algebra and using the Poisson approximation, we can show that odds here increase exponentially with K and decrease exponentially with n, which is what you would expect. So again, remember, K is the number of times I saw the particular extraction. How many times did I see that Los Angeles is a city? And n is the total sample size. I'm sorry? What was S? Let me gloss over that for now. Now it turns out that it's easy to, the reason this model is called the Urns model is because really each extraction rule has multiple urns. And again, remember this intuition that an error is likely to show up in some urns, but probably not all, whereas a correct extraction like cities would tend to be common to all rules. So that means that the correlation across these distinct urns of the correct names is going to be much higher than the correlation of the errors. And again, the math gets more complicated, but the bottom line is it allows us to compute these probabilities very effectively and directly off of B's extractions. Okay? And to give you a sense of how much better this is than what we had in the past, here are a few relations, and this is on the y-axis a measure of how correct our probabilities are. And you can see that when we compare it to the noisy OR used in previous work or to PMI used in our own work, the deviation from the ideal probability, okay, and this is actually a log scale graph, so it's even more than you think. The deviation that we have in the dark black with Urns is very minimal, and the deviation that these other methods have is huge. So we've gotten a 15x, 15-fold improvement easily over previous work. And we get to have a system which we call KnowItNow, which is simply Urns plus B. B is used for the extractions. Urns is used for the assessment. And I want to show you how KnowItNow works. This is on an index of 90 million pages at precision 0.8. And what I want to show you here is the comparative recall. Because remember, still one of the issues here is compared to going to Google, is Google's got a much larger index. So how are we doing on recall? And it turns out the answer is pretty well. Again, so if you see on the y-axis is the number of instances extracted, and on the x-axis a bunch of different relations. And we're definitely not finding more than Google, sometimes quite a bit less, but still it's pretty respectable. If you look at the time figures, and let's see how am I doing on time. I'll skip the details and just jump to the punchline. Things that used to take 33 days using KnowItAll now take on the order of 3 minutes using KnowItNow. And let me see if I can invoke this to show you a demo. So KnowItNow still takes close to a minute to do its thing. So what I'm going to show you are queries that are cached. So it's not quite as blindingly fast as you might think. But here's a query. Again, Ed in his continuing sort of dog and pony shows had me meet with Jeff Bezos for 1.3 minutes. And so I asked him to give KnowItNow a query. And he said, OK, try deities. And you see that, so I did. I had no idea what would happen. And you see that Vishnu, Shiva, a bunch of Isis, a bunch of deities I never heard of are represented here quite respectively. Let me do another one that's fun, and that's insects. And again, you see it does a pretty good job of finding things that are said to be insects. I showed this to some crowd, and people started telling me that some of these things are not actually bona fide insects. So remember, these are not all bona fide insects, and Elvis did not kill JFK. We're just working off of the corpus. One last example, because it's fun. I just earlier today, hopefully it'll still be in its cache, typed in programming languages. And here's what came back. So again, it's not perfect, unless Plus is a programming language that I missed. Nevertheless, and again, I mean, you see sharp here, right? That's probably some kind of part of speech tag error, right? I mean, it's obviously referring to C#. OK, so I'll open this up later if people want to do their own queries. This is also accessible on the web, so if you want to disrupt the research that we're doing for our paper deadlines, just find it on the web and issue your own favorite queries. OK, so what's wrong with KnowItNow? If you remember my family tree, we've got one more system to go, which is TextRunner. But who needs TextRunner given that KnowItNow is getting the laughs? Well, KnowItNow is pretty good at giving you instances of classes. Appropriately configured, it'll also give you relations. So if you want city-mayor pairs, you can do that. But there's a bunch of things that it won't do. First of all, it's extremely wasteful. It ignores most sentences. It's not able to extract information from most sentences. Only uses a very limited set of patterns. Secondly, if you ask it for more complicated items, like Woody Allen movies starring Mia Farrow, really any conjunction, it will have a much harder time with. And it doesn't support inference. Let's say you're looking for an American scientist and somebody tells you that Oppenheimer is a Berkeley physicist. It's not able to make that connection. It does no inference of any kind. And as you might guess, TextRunner addresses most, if not all, of these limitations. So TextRunner is the most recent work. And this is work by Michel Banco, Mike Caffarelli, and myself. And the basic idea is to try and extract textual triples from most sentences. The idea is if you go to a sentence, there should be a way to extract some information from it. And as an incredibly crude approximation that does no justice to Michel's work, think of subject, verb, object. Okay, something, you should be able to get that out and then you've learned something, right? From pretty much every sentence. What we do is actually infinitely more complex. It's actually a self-supervised learning mechanism that's quite sophisticated, but I don't have time to go into it. Anyway, what we do get from sentences are these triples, like Berkeley hired Oppenheimer, or a physicist is a scientist. And this turns out to be very much a superset of what you find in KnowItNow. And what we do with these triples is we put them together to create really a kind of approximate entity relationship graph off of the entire corpus, 90 million pages. And the reason that I say it's approximate is because the nodes here are strings that name entities and classes. The edges here are also strings trying to capture the relationship between these entities, like hired is the relationship between Oppenheimer and Berkeley. But this graph is built automatically from text, which means that we can't make strong semantic guarantees on the triples, right? So we'll find things like Einstein died in 1955, and we'll put that happily along with A. Einstein died in 1956, even though these triples are obviously inconsistent, right, to the human eye. So we're not going to make any claims about consistency here between these. We're not going to make claims about that we're picking out individual entities correctly. There are a lot of problems with synonyms, with aliasing, inconsistency, et cetera, et cetera. This is a very noisy graph. But what we do hope is that redundancy will enable us to cope with some of this noise. And it turns out that we can actually do at least simple forms of inference over this graph. So here's how the simple form of inference works. Let's say we have these 4 documents or 4 sentences extracted from documents. So Oppenheimer worked as a physicist. He taught at Berkeley in the 20s. Scientists include physicists, and Berkeley, California is in America. So each of these would lead to a triple that's represented in this graph, like Oppenheimer taught at Berkeley. And it turns out now that if I ask a query for an American scientist, and right here, nowhere does it say that Oppenheimer is an American scientist. What the system can do is basically spread activation or energy or whatever you want to think of it from America, which is in the query, or American, and from scientist. And when it does that, they meet at Oppenheimer, and it concludes that Oppenheimer is an American scientist. So again, this is very, very rough and ad hoc. And something that Mike is doing right now with Dan Suchu's help is thinking about how you could assign a probabilistic semantics to this process or to a modified version of this process. So we're not just playing with strings. We're trying to think about how you could actually do normatively correct probabilistic inference over these kinds of graphs. The thing that delights me is that TextRunner is quite effective at extracting information from the web. So out of 90 million pages, we've gotten over 1 billion triples. Our extraction yield is roughly 1.2 per sentence. So we actually can get sometimes more than a single triple or fact out of a sentence. We can do it pretty quickly, 0.65 seconds per document. And again, I think we can easily optimize that. Our precision is 68.5, which is somewhat low, right? So this graph is very noisy, but again, we're now just starting to improve this precision. So lots of open problems here to improve the precision recalls I mentioned, to deal with synonymy and polysemy. These triples are only encoding binary relationships here, right? So we need to generalize this to n-ary relations. And I mentioned probabilistic semantics. Also, we want to generalize from TextRunner's content, right? So we have a very large number of facts. Can we look at those and start to form generalizations, again, ones that are not explicitly stated in the text? Effectively, can we learn a theory based on, based on what's said in the text? So let me conclude with these observations, and then I'll try to get that demo going. You know, KnowItAll, I was reading the KnowItAll paper before today's talk, and we very proudly announced in 2004 that KnowItAll extracted 50,000 facts from the web. So in now 2006, we're up to 1 billion facts. So that's a good factor of 20,000 increase. Feel pretty good about that. Our precision has dropped, again, to roughly 0.7. So some work to do there. Another thing that's even more important is that one of the distinguishing features of KnowItAll is that it required no hand-tagged examples. Okay? The reason for that is we want to scale to the web. We want to scale to the variety of queries somebody might issue to a search engine, variety of information needs. So you can't assume that this system has hand-labeled training examples for the particular concepts of interest, right? That doesn't make sense. So that was a very nice feature of it. However, if you were listening closely in the beginning, you'll see that we did say you have to give it as input the target relations, right? You say, okay, go find me cities or movies or COs. And we also gave it these generic extraction templates. The problem with these is, again, they very much limited the set of extractions it was able to do. So, of course, we could have given it more, but that's a lot of manual labor, right? We gave it about 8 to start, and maybe it needs thousands and thousands to achieve really, really high recall. In contrast, TextRunner is what I like to call self-supervised systems. So those of you familiar with machine learning, right, there's supervised systems. They're really very heavily controlled by a human. There's unsupervised systems like clustering algorithms that just try to find structure in data, but don't really attempt to in any way compete with supervised systems, right? It's just a different task. A self-supervised system is one that generates its own training examples, labels them itself, and in the case of TextRunner, even comes up with its own concepts. Okay? TextRunner decides what to do. Okay? It decides what to learn, and it decides how to learn it. So really a very unique system. And the fact that it has that level of autonomy means that it can run very rapidly at scale over arbitrary web text. Now, you might ask me, if you're clever, well, okay, so each of the systems you showed us had a kind of Achilles heel, right? So what's TextRunner's Achilles heel? And TextRunner's Achilles heel is that it suffers from attention deficit disorder. Okay, it goes through the web and says, oh, here's a sentence. Oh, there's a fact. It's very happy to extract just a tremendous amount of random nonsense. And so, again, getting TextRunner to settle down and focus is our topic for future work. Dan.
So at least as you presented everything here, every web page and indeed every sentence is treated equal. No preference based on link structure or page structure or anything. Is that a religious principle or just future work?
Future work. That's a good idea for future work. And it could affect credence as well as importance. And that's definitely something that we need to do. Mike, are you writing this down? No, I'm joking. It's on our list.
Now, this is maybe a follow-up question related to deceptive web pages. So one phenomenon is Google bombing, where people will cause associations to come up. For example, a few months ago, miserable failure led to a certain politician. So one answer you could give is, well, that's just the structure of the corpus, and so we reflect it. But maybe a more interesting one is doing some sort of machine learning or other techniques where you learn these patterns of deception and can filter them out.
I think that is incredibly interesting, and I haven't spent time thinking about this. Although people have pointed out in the past that there's a certain we need to take responsibility for what TextRunner is believing, and it's interesting to think about how to match it up with reality. Of course, some of those Google bombing statements are actually true.
Just to extend on that, I mean, your system's running as sort of a truth by democracy, and I can't remember who it was who said that democracy is a terrible system, but it's the best we have. And I wouldn't be surprised if you found that it does work quite well to either be somewhat democratic or not overly trust certain sources than others.
Absolutely. The only claim that I would make about our system, and this is what we're working towards, is that it attempts to be truth preserving. Right? And again, we've run it on the web corpus. You could imagine running it on more high-quality corpora as well, where again, you get commensurately better results. But absolutely, we need to work on truth. Yeah.
So you've presented some simple facts, things like where there was easily encountered extraction phrases like city such as. Did you find a lot of facts where it was sometimes hard to find a good extraction phrase that occurred a lot? Because it seems like in a lot of writing, when I encounter on the web, there's sort of more novelty in the use of words and such.
Yeah. So that's actually the beauty of TextRunner. I haven't been able to make that explicit, so thank you for the question. TextRunner leaves those extraction phrases behind. It uses a much more free-form system of analyzing the sentences and looking at minute syntactic features of the sentence to decide, okay, this is a semantic triple. So that's really a huge advance for us, and that's what allows us to go from, a month to get 50,000 things to getting a billion facts.
I'd add to that there are certain kinds of relationships that English doesn't seem to reflect very well at sort of the local scale. The TextRunner, even the TextRunner system, doesn't do very well at distinguishing descriptions of fiction from descriptions of reality, just because there don't seem to be sort of easily encapsulated per sentence statements about that.
Right. So, some of the work, for example, done at the Intel lab, right, we're really still thinking about reading at the sentence level, right? What if you have a process description, like a recipe, right, with a sequence of steps? We're not thinking about that. We're not yet even dealing with pronouns. Yes?
So what's the performance, the efficiency, and scalability of the TextRunner? And what indexing system are you using? Do you use BE?
TextRunner is built on top of Nutch. So Lucene is the indexing system. And the performance, I guess you're asking, how long does it take to generate the index? So I show the figure of 0.65 seconds per document on average. A few seconds. The reason I'm not showing the demo, because I have absolute faith in Mike that it's up, is I'm missing the URL. I didn't bring it with me for this. And it's a strange URL. But let me not do URL hacking right now. If you come down afterwards, we can play with TextRunner.